So I'm Alastair Thomson. I have the privilege of serving as the Chief Information Officer at the National Heart, Lung and Blood Institute at the National Institutes of Health. Some of the biggest ones coming down the pike are genomic sequencing, whole genome sequencing. The cost of sequencing a human's genome was $3 billion in about 2000. It's now less than $700 per person. And so suddenly we've got the ability to focus very precisely on treatments for patients, but it involves a lot of data. In our Transomics for Precision Medicine program, TopMed, we've now got the largest group of human genome sequences in the world, 130,000 people. That's about 1.7 petabytes of data that we're dealing with. But it's tremendously helpful because as the prices come down, we can sequence someone, we can compare their DNA to everyone else in that group and find out what are the correlations for their diseases versus the ones that we see in our studies. Some of our studies, like the Framingham Heart Study and the Jackson Heart Study, have been going for decades. We're working on what are the things that are going to design the best treatments for it based on your genes, not just on the symptoms that you see. It's been an interesting several years. The acceleration of the generation of data has been phenomenal. NIH, we tend to lead where industry is going to be by a few years. So we're dealing with the challenges of how we deal with that massive amount of data now. Healthcare providers are starting to see it, but if they see it at the rate of growth that we are, they're going to have some significant problems if they don't change the way they deal with things over the next few years. That means they're going to have to move to the cloud aggressively because it's the only place that you can store and compute on 1.7 petabytes of data, or in their case it could be even hundreds of petabytes of data to be able to generate those personalized treatments. We've got about 22 million chest CT scans from patients with COPD. We also have their genomes. So we're trying to use machine learning to develop a means to look at those CT images and look at their genome and predict what the progression of their disease is going to be, what kind of progression it will be, the treatments that might be made available. And that's going to happen all across what we do. One of the big challenges we have with a lot of our data is that it's unharmonized. But machine learning has the potential to be able to filter out that noise that is the unharmonization and actually work with the data directly. That will markedly reduce the cost of bringing together data sets historically and going forward. And the more data you have, the better these machine learning models can work. And we see it as not just a way of predicting treatment, but of actually understanding what the long-term prognosis is going to be for patients and help them to make life decisions in an informed way. We also behave a lot like academia, where our fundamental goal is to share data, share information with collaborators. Some of those collaborators come from nations that are not that friendly to us. And yet I've got to balance the confidentiality and integrity and availability in a way that we keep patient data protected, that individuals who are participating in human trials, their data is protected and safe, and yet it's able to be shared with people, with scientists all over the world. In keeping those things balanced, I need to deal with the fact that I have people from all over the world who need to access data, but in a very controlled way. Not just in terms of protecting the data, but respecting the consent of the patient who provided that data. And we're looking to technologies like blockchain to hold those consents, allow an immutable record of who's done what with their data, both to protect the data and to empower individuals to control who uses their data and who doesn't. And all of that has to be woven into all of the usual compliance that we have to deal with. It makes it for a pretty challenging environment. I think one of the most exciting things we're doing is called the NIH Data Commons, and NHLBI has a sub-project called Data Stage. This is fundamentally about dealing with the massive growth of data. We're working with a group of about 500 people from research institutions all over the world to develop a cloud-based environment where massive amounts of data can be stored, and then they can compute and analyze that data. There's a lot of things that we don't know how to do. And so we've got teams from academia, we've got teams from the commercial world, and via the recently signed Strides agreement with Google, we actually have Google, and we hope to have Amazon and Microsoft and other cloud providers participating in this too. So they can bring their expertise and technology to help solve some of these, the most critical problems. Today in science, data is locked up in individual research institutions' data centers. Great data, but no one can get to it other than the researcher who created it. In the NIH Data Commons, that'll be available to anyone who has the need to use it and can comply with the consents. That's unheard of. It's going to make an enormous difference to the progress of research. It's going to enable fundamentally new techniques to be developed in ways that have never been able to be done before. These partnerships with companies like Google, who have developed techniques for dealing with the massive amounts of data. But it's also about dealing in new ways on the biotech side of it. We have a new initiative called the Cure Sickle Cell Initiative. It's a terrible disease. It causes chronic pain. It causes acute issues of pain, episodes of pain in people's lives, and yet we don't have many good treatments for it. The Cure Sickle Cell Initiative is aimed at using all of that information we have from whole genome sequencing, from gene editing, from other techniques like bone marrow transfusion, and use all of that information to guide us to something which is actually a practical cure for a disease that affects hundreds of thousands of American citizens as well as people all over the world. The foundation for that is technology. It can't be done without the IT that supports it. Providing computational resources on those massive data sets to researchers. We have over 1,000 researchers currently working on our TopMed program. But again, they're struggling to deal with all of the large amount of data that we have. So providing storage for that data, both for our researchers on the NIH campus in Bethesda, where we have 72 investigators doing incredible things, but they need incredible amounts of storage. The generation of data is great. Making it available and usable to people is probably our biggest challenge outside the cybersecurity and protection of patient data. We're dealing with, as I said, very large amounts of genomic data. There are some real challenges in just managing that data. We've had to build expertise that just doesn't exist. We've had to build technologies that allow us to access that data in an efficient manner on the cloud. And those are the same problems that are going to be faced by healthcare providers, insurance companies, everyone who's involved in the healthcare industry. And so our research is no longer just biomedical. We're actually making discoveries in computer science, systems engineering that are going to guide where those healthcare providers are going to have to go. And again, there's millions of petabytes of that data out there. The only ways we're going to be able to deal with that are using techniques like machine learning. And this is one of the things that the All of Us program at the NIH level is looking at. They're bringing in EHRs for 1 million people, along with the genomic information and all of the other things. And so we're working with them on some of these techniques that in the end are going to end up in industry. The machine learning models we're building for COPD treatment, those ML models are going to need to be executed in hospitals. That's a very different way of dealing with medicine. There's cultural change that's going to be required to do that because clinicians are going to have to not only just trust their own judgment, but they're going to have to start to trust the judgment of systems that you can't really explain how they work.